projection at an angle to the horizontal. So we're going to continue with our work on projectiles, but this time we're going to look at the slightly more complex scenario of when particles are projected at an angle above the horizontal, so they're not projected purely horizontally. Let's set up the situation. So our particle is projected at an angle theta above the horizontal. So let's draw in the velocity of the particle, the initial velocity of the particle, with a speed u meters per second. So u is the magnitude of this velocity, and we'll label that there. It's an angle theta above the horizontal, like that. Now what we're going to do is we're going to draw in the two components of this velocity here. There's a horizontal component like that, which I'll draw in green, and a vertical component like that, which I'll draw in yellow. Now, think about when you resolved forces. You can resolve a velocity in the same way using the ideas of vectors. So the horizontal component here, the green component, is the initial horizontal velocity or initial horizontal speed, which is u cos theta. And this vertical component here in yellow is the initial vertical speed or vertical velocity, which is u sine theta. So we now have this information. So this time we see the full parabolic path of the particle. Let's assume it's starting here at the origin. It decelerates upwards until it reaches this point here, which for the moment we'll call point A, which is its maximum height above the ground. Now, as the particle travels, think about the forces acting horizontally. There are no forces acting, which means there is zero resultant force and zero horizontal acceleration, which means horizontally the particle travels with the same horizontal speed as it had when it started. So u cos theta is a constant horizontal speed. Let's pick a point for the particle here, and let's draw on its velocity vector. Now, its horizontal component will still be u cos theta at every point on the journey, but the vertical component will have changed. So we established that the particle decelerates up towards the point at which it has its maximum height above the ground. Now, at this point, the particle still maintains its horizontal velocity of u cos theta, but it has zero vertical velocity at its maximum height. After it has reached this point, the particle then accelerates down towards the ground, and we'll call this point B the end of its journey. Remember, the acceleration vertically is the acceleration due to gravity because, of course, vertically the only force acting is the weight, and essentially as the weight is the resultant force vertically, the acceleration which is generated due to this weight is the acceleration due to gravity, which is 9.8 meters per second squared, or g. So as we've done previously, to analyse the motion we would split this into two components or two directions. We'll look at the horizontal motion, and separately we can look at the vertical motion. So I'm assuming that we are looking at a journey starting from O onwards to another point. Let's investigate what we know horizontally. So, as previously in the model, we assume that air resistance or drag is negligible, so there are no horizontal forces acting, which means there is zero acceleration horizontally, which means the object is travelling with a constant speed, and the constant speed is equal to this initial horizontal speed, which is u cos theta, the horizontal component of the velocity of projection. Now, vertically, what do we know vertically? Well, we know that the only force acting is the weight, which is constant. So there is constant acceleration, which is equal to the acceleration due to gravity, g. And we can apply our Suvat equations. Now, one thing that is a little bit different when we're dealing with projection at an angle to the horizontal is because the movement of the particle is initially upwards, and because the displacement it covers is vertically upwards above ground, it makes it easier to choose up as the positive direction. Of course, this will have an effect on the acceleration when you're applying the Suvat equations, but we can handle that. So Suvat, if we're working vertically, S is question mark. It's something we might have to calculate depending on which position we're travelling to. U is equal to our initial vertical velocity, which is u sine theta, assuming of course that all of the motion is starting from the origin in this particular example. V is question mark. Again, it depends on which point we travel to. A is going to equal negative g, because of course the acceleration acts downwards and we have chosen up as positive. And t, the time taken, again depends on which point we have moved to. We can still solve problems in the same way that we've done previously, we just have to bear these changes in mind. So let's go straight into example 1 and label a diagram based on the information in this question. We have a particle projected from a point O with a speed of 30 meters per second at an angle theta above the horizontal. Now, we're told that sine theta equals 3/5, which is quite an interesting piece of information. We can obviously use inverse sine on our calculator to work out what theta is, or we can quite nicely draw in a right-angled triangle. If sine theta equals 3/5, that means the ratio of the opposite to the hypotenuse would be 3 to 5. And using Pythagoras' theorem, we can very easily see that the third side would have to be 4 to make the ratio work here. 3, 4, 5 triangle. So we can then write down that cos theta equals 4/5, and it's useful to have the exact forms here. So what else do we know? We need to find the greatest height above O reached by the particle. So I'm going to call that point here P. And the horizontal range of the particle, which I'm going to call the distance OQ, so how far it travels. So let's draw on a line to represent the acceleration due to gravity, g, which looks like that. And then I'm going to draw in the components of this initial velocity, 30 cos theta here, and then vertically 30 sine theta. Now, because I know what cos theta and sine theta are equal to, I can simplify these. So 30 times cos theta is 30 times 4/5, which equals 24, and 30 sine theta is equal to 18. So we have our two components in place, ready to go. Now, for part A, we want to look at finding the greatest height above O. So we're going to look at the journey from O through to P. So what do we know? From O to P, I'm going to look at the vertical motion because I don't really know much about the horizontal movement from O to P. I don't know the distance between O and P horizontally. I don't know the time taken to reach P. So I'm going to look at the vertical motion. Now, I'm going to choose up as my positive direction. So S is equal to this height here. We'll call it Y. U is equal to 30 sine theta, or 18. V. Now, at P, we know that the vertical velocity is equal to 0 because P, of course, is at the maximum height. So V equals 0. A equals negative G because A is downwards and we've picked up as the positive direction. And T is a question mark. We don't know what T is equal to. But it is Y that I need to calculate, or S that I need to calculate. So using these four variables, I can use V squared equals U squared plus 2AS. 0 equals 18 squared. And then we can rearrange this equation to calculate y, which comes to 16.5306 metres, or 16.5 metres to 3 significant figures. So part B asked us to calculate the horizontal range of the projectile, i.e. how far it travels horizontally by the time it hits the ground. Let's split the motion up. So horizontally, we know that speed equals distance over time. Remember, we're focusing on the journey from O through to Q, and we've written that down as well. So the horizontal component of the velocity is 24. And this is equal to the distance travelled, which we'll call OQ, divided by the time taken. We don't know the value of that time. Now vertically, from O to Q, choose up as positive. Now S, the displacement, is equal to 0, because at Q, we're on the same level as at O. U, we know, is equal to 18. V, we don't know the value of V at the point Q. A is equal to negative g, and t is equal to the time taken, the time of flight. So let's exclude vq, or velocity, from our calculation, and with the remaining values we can use s equals ut plus a half at squared. So 0 equals 18t minus 4.9 t squared. We can factorise this quadratic equation. Take out the t, like this, and then of course we get t equals 0, which is not the solution we want. That's when the particle is at its starting point at the origin. But the second answer that we get, t equals 18 over 4.9, that's when the particle is at point Q. And what we're going to do is use that to work out the horizontal range. So we'll substitute this value, which is equal to 3.673 ... into this equation here. So we can work out that OQ is 24 multiplied by the time taken, which comes to 88.163, or 88.2 metres, to 3 significant figures. Let's move on to a more complex question. A girl hits a ball at an angle theta, where tan theta equals 3/4, from a point O, which is 0.5 metres above the ground. So careful with your wording. The point O is here. And if we draw in a horizontal like this, the ball is struck at an angle like this above the horizontal. And we know that tan theta equals 3/4. And again, if I sketch a right angle triangle with theta, tan is the ratio of the opposite side to the adjacent, so that means that we can have a combination 3 and 4 here. It's a 3, 4, 5 triangle again, so I can very simply work out cos theta is 4/5 and sine theta is equal to 3/5. Now, the point O is 0.5 metres above the ground, so that's this distance from here to here. The initial speed of the ball is 15 metres per second. And it just clears a fence, which is a horizontal distance of 18 metres from the girl. So let's draw in this fence. Now we have no idea exactly where this fence is going to be. It doesn't really matter in our diagram. I'm going to position it here, and I'm going to say that this measurement here is 18 metres, and I'll call this point here A. So let's mark on the acceleration due to gravity downwards, g, metres per second squared, and let's split the motion into horizontal and vertical components, looking at the journey moving from O through to A. So horizontally, first of all, we know that speed equals distance over time. We haven't written in these components of the speed, so let's go back and do that. So there is a component horizontal of the speed, which is 15 cos theta, and a component that is vertical, which is 15 sine theta. Now our horizontal component, we can simplify 15 cos theta using the value up here. So that comes to 12 metres per second, and then 15 sine theta comes to 9 metres per second. So horizontally, we know that speed equals distance travelled over time taken. So horizontally, The constant speed is equal to 12, and the distance from O to A we know is 18, so we can then from there divide that by the time, and we can work out that the time comes to 1.5 seconds. So at point A, time is 1.5 seconds. Vertically, let's look at the motion. So again, from O to A, we'll take movement upwards as positive. Now it's important to note that the way that I'm doing this question, I'm taking this point here, O, as my origin. So this becomes the baseline for my measurement. So when I calculate my displacement, it's going to be relative to this point O, not this point over here. So vertically, S equals, let's call it Y. In fact, I'm going to mark it on here as Y. U is equal to 9. V is equal to V at A. We don't know what that is. A is negative G. And T is 1.5 seconds. We now know this value. So ruling out V, as we don't have that information, we again come back to S equals UT plus a half AT squared. So Y is equal to 9 times 1.5, etc. And then calculating Y, this gives us an answer of 2.475 meters. Now, that is this measurement here. Let's highlight it so you can see it really clearly. This distance here is the 2.475 meters. So it's 2.475 meters above this zero level. So in order to actually work out the height of the fence, we need to add on this 0.5 here. This is not to scale. I appreciate that the 2.475 looks tiny compared to the 0.5. Don't worry about that. Do another sketch diagram if it helps you, but don't think that the measurements in this diagram are to scale, because they are not. So the height of the fence is equal to 2.475 meters plus the extra 0.5, which gives us 2.975 meters. Now, there is another way of doing this question if you want to take this point here as the origin, which I've just shaded in red there, and we can do that. If you want to do this, then you're going to have to use an adjusted Suvat equation. We saw an example of this last time in the previous lesson on this. So S equals UT plus a half AT squared plus S0, which represents the initial displacement. Now, if your initial displacement is 0 because you're at the origin, this then turns back into S equals UT plus a half AT squared. But we did not start this journey off at the origin. We started this journey with an initial displacement of 0.5 meters. So S then equals U, which was a value of 9 multiplied by T, 1.5, plus a half times negative 9.8 multiplied by 1.5 squared plus our initial displacement of 0.5, and you will find, unsurprisingly, we get back to 2.975 meters. It's just an alternative way of doing the question. So this time I made the origin, the actual origin, rather than my starting point. Let's look at example 3. We have a ball projected from a point O at the top of a cliff with a speed v meters per second at an angle of 30 degrees above the horizontal. Let's fill in that 30 degrees there. The greatest height reached above the horizontal through O is 4.9 meters. So that's important. It's the greatest height reached above the horizontal through O. So this is the 4.9 meters. It's not being measured relative to the ground. We also know later on that O is 60 meters above the surface of the sea, like that. And we're being asked to find the time taken for the ball to travel from O to the sea's surface here at B. Let's mark on the acceleration due to gravity g, and we're going to get duck in straight away to the first part of this question, analysing the motion between O and A. Starting off horizontally, we know that speed equals distance travelled divided by time taken. So let's draw in our components. We know that there's a horizontal component, which is v cos 30, and a vertical component, which is v sine 30. Of course, we know the values of cos and sine 30, which would be very useful. So horizontally, the speed v cos 30 equals the distance travelled from O to A. We don't know that. We'll call it x. And that's divided by the time taken, and we don't know that either. Let's look at the vertical motion from O to A. So S is equal to, well, before we do that, let's define up as positive. S equals 4.9. U equals V sine 30. V equals 0, because at A the vertical velocity is 0. A equals negative g, and t we don't know. So we can discount t from this, and we can use the rest of the values we have here, and the Suvat equation, v squared equals u squared plus 2as. So sine 30 is a half, so this is a half of v. So what do we have? We have 0 equals half v all squared minus 2 times g times 4.9, and from here we can rearrange and solve, and we will find that v equals 19.6 meters per second. So we've answered the first part of the question. We're now going to look at the motion from O through to B. So from O to B, let's analyse the motion horizontally, and let's analyse the motion vertically, and remind ourselves that we need to find the time taken for the ball to travel from O to the C's surface. So horizontally, the speed is v cos 30, which equals the distance horizontally, which we will refer to as just distance for the moment, divided by the time taken, which we don't know. So horizontally, although we know v, we don't know the distance or the time, there's not much we can do. Vertically, defining up as positive, S, U, V, A and T, S is equal to negative 60. Now, why is that? Well, let's go back to the diagram to make sure that we understand this. So if you think of this as a set of axes, the trajectory of the particle looks like that. Now, we're effectively treating this as a sort of an origin, and this distance here is 60 meters, so by the time we hit this point here, relative to this horizontal 0 level, we're 60 meters underneath it. We defined up as positive, which means our displacement is negative 60, because we're 60 underneath this sort of temporary x-axis that we've created. U was equal to v sine 30, which we can now calculate as 9.8 meters per second. V, the velocity, we don't know what the velocity is at B. A is equal to negative g, and t, the time, is what we're actually looking for. So let's discount v here, and then use s equals ut plus a half at squared. So negative 60 equals 9.8t minus 4.9 t squared. So rearranging that, 4.9 t squared minus 9.8 t minus 60 equals 0. And of course, we clearly have a quadratic equation here, which you can solve on your calculator or using the quadratic formula. You will find that you get two t values, of course. T equals negative 2.639, which is not a real solution, ignore that. And t equals 4.6393, which gives us our correct answer of 4.64 seconds to 3 SF, okay? Remember, t has to be greater than or equal to 0. This sort of extra solution here comes from the geometry of the graph. If you tracked back this quadratic function, you would get an x value here, which corresponds to negative 2.66 ... of course it's not really a practical answer in the context of time. Right, example 4, which has been chosen because it includes vectors. A particle is projected from a point with position vector 3i plus 3j. We're going to assume I and j look like this, relative to a fixed origin O. 2 seconds later, the particle passes through the point with position vector 13i plus 8j. So this point here, we'll call it B, this point here we'll call A, and this point has position vector 13i plus 8j relative to the origin. So if we were drawing these as coordinates, this would be 13, and up here, this would be 8. Find the initial velocity vector. So there must be an initial velocity projection, which we will, for the moment, refer to as U, capital U, vector underlined. Let's draw on the direction of the acceleration due to gravity, which is g. Now, if we wanted to write g as a vector, we can do that. It would be 0, negative 9.8, because again, j is defined as being upwards, or negative 9.8j. So we're going to analyse the motion from A through to B, and just to do this a little bit differently, we're going to consider both the horizontal and vertical directions together by treating this as a vector problem and using the vector as a whole, both components simultaneously, rather than splitting up into horizontal and vertical motion. You can still solve this the same way that we have done the previous questions, splitting up into horizontal and vertical motion separately. It's very similar to the last question, but we're going to look at a different approach because it's good to see these different methods. So let's remember that we are looking at the motion from A across to B. So this time, when we write down our SUVAT information, it's going to be in the form of vectors. Now, the movement from A to B, 3 moves to 13, 3 moves to 8, it's a vector of 10, 5, okay? Remember, the point A has a position vector of 3, 3, and the point B has a position vector of 13, 8. So if you're looking at the vector that goes from A through to B, it of course is the vector 10, 5. Now, our initial velocity vector, u. So we referred to the initial velocity as capital U, and it was an angle of theta above the horizontal, let's say. So our horizontal component is u cos theta, our vertical component is u sine theta, and we can fill those in here. Now, v. I don't think we know anything about the velocity at B, so we'll ignore that one. A is, of course, our acceleration vector, 0, negative 9.8, and t is the time taken to reach point B, which is not a vector. Time is a scalar quantity, so t equals 2 seconds. So, which SUVAT equation would apply here? Well, let's cross out V, S, U, A, and T. We can use the SUVAT equation S equals ut plus a half at squared, writing the different parts of this as vectors. Let's fill in what we can. So 10, 5. I'm doing this as column vectors because I think there can potentially be some confusion when we introduce all the i's and j's. It's exactly the same thing, and this is just a little bit clearer. So we have a half, 0, negative 9.8 multiplied by 2 squared. So what can we work out from here? Well, we need to know what u cos theta and u sine theta are, because then we get the two components of the initial velocity vector, so we have to do some rearranging. So I'm going to look at the I components first of all on the left and right side of this equation. So we've got 10 equals 2u cos theta, and there's no I component from the second part of this. You can see the I component is 0. So this then gives me that u cos theta is equal to 5. Let's now look at the j components. So the I components, just to clarify in case anybody wasn't sure, I was looking at these. For the j components, I'm looking at these parts here. So let's finish that off. So 5 is equal to 2u sine theta minus 19.6, and I can rearrange that to give me u sine theta is equal to 12.3. So I now know the two components of my velocity vector, u, which is equal to 5 and 12.3. We could also have done the whole question using this version of the Suvat equation, s equals ut plus a half at squared plus s0. And this time, the displacement, of course, we're measuring everything relative to the actual origin, not our starting point. So we measure s and s0 relative to 0, 0, not a, like we did in this example here. So s, of course, would then be the position vector of b, which is 13, 8. U is still our velocity vector, u cos theta, u sine theta multiplied by 2, plus a half of the acceleration vector, 0, negative 9.8 multiplied by 4. And we have to add on our initial displacement for a. So this vector here is, of course, equal to the position vector of a to begin with, so that is 3, 3, and you can see straight away when you subtract the 3, 3 vector from both sides, you will actually come straight back to this vector equation here. So it will work out to give you the same answer as previously.